I believe we are live. Welcome everybody to part 2 of segment 3. Here we will be discussing lazy propagation or range updates. So you may know we have studied about how to build a segment tree, how to query on a segment tree, how to modify the segment tree for sum, for max, for min. I will show it to you. For example, this is where we have left in our last class. So this is basically, let's forget the debug part. So what we had is initially we had we discussed this build function, and we have said that how to build this. For example, in our case it was sum tree, right? So we have said that okay, if we are on the leaf node, the answer is just the L part of our array. If it otherwise we build the right left part and the right part, and then we combine our result from the left and the right. So this is called the combined logic. Okay, and this combined logic is very important. Like this combined logic will be, for example, this is the addition. So it will represent sum tree or segment tree that is used to query on sums, update sums. Similarly, in query also, you see that we have returned left plus right. So this is again the combined logic. Like if you are doing finding maximum in a range, then this will be max of left and right. Okay. Also, there is the base case logic that what if I am in the end? What should be the answer? Like if L and R is same or completely within responsibility region, what should the answer be? Like if it is outside, uh, we say we return something called a zero because that does not affect our sum. If it were minimum, we would have said return the maximum value so that minimizing that with our actual answer does not change the my answer. I think we have discussed this in our previous class that how to select or how to choose between what should I return if the intervals are disjoint? What should I answer if my responsibility region, which is L to R, lies completely within my query range? Okay, so this is the sum tree. Okay, I will make a new file. Let's call this file part one sum tree. Uh, Similarly, I can just say that I can just copy this and then I will just call it that part one. Let's call this the minimum tree. So what the change I will make here is if I am in the leaf node, then my answer is just the element. Either it's minimum or maximum. Otherwise, you see that after the left and right part is built, I want to combine them as the minimum of left and right. Okay, this is called the combination logic for this would be the combination logic for minimum. Uh, if I am completely within, I will call it, okay, let's call it the min tree. Okay, so this is the combination logic. If I'm querying and if I'm completely within the bounds, then we just return the answer. If it is disjoint, I should return some big value. Let's return int max because if int max is minified with my current answer, for example, this right part returns int max, then minimum of left and right will not change my answer. I hope this is making sense. Okay, you can test these code. So this will be the minimum tree, and the maximum tree will just be Okay, I think we have made a sum tree copy. We don't want that. We want the minimum tree copy. Yeah, let's call it the max tree. So in this case, the only change that I will make is calling this main tree as max tree. And we will say that in this combination logic, we will not select the minimum, but the maximum part. And if I have disjoint, we will return some very less value or very minimum value. So what we have done is if I disjoint, I return a minimum value such that maxing it here does not affect my original answer. I hope this is making sense. So we have learned how to create sum tree, minimum tree, maximum tree. You can also create GCD tree. In this case, you know that doing GCD with zero doesn't change the answer. So in this joint case, I should return zero. In combination, I will just take the GCD of left and right. And here I will take the GCD of left and right. I hope this is making sense. Let's make the GCD tree as well. So, okay. So what the change will be? First, we call it a GCD tree. And I will say that if I'm completely disjoint, I should return zero. You see, I'm making small changes. Let's see how the stream is running well. Yeah. So you see, I'm making small changes, and that constructs different types of segment tree. Minimum, maximum, GCD, XOR. Basically, any associative function can be implemented through segment trees. You understand that subtraction is not associative in nature. Like a minus b minus c, if you do a minus b first, or you do b minus c first, that leads to different answers. So we cannot do it. Okay. Okay. Wait a minute. Disconnected by mistake. Anyways, so you understand that. So we can also make the XOR tree as well. In this case, let's call it the XOR tree. In this case, you may know already the answer that if I'm on the leaf node, the XOR of A and A, what should the answer be? Like for example, uh, let's say if someone asks me the XOR of 1 to 1, that's just one element. It's not that XORing 1 with 1 itself. Let me show you this on the code. For example, let's say 1, 2, 4, 5, 6, 9. What if someone asks me the query, what is the XOR between this? Should I answer 0 or 1? I should answer 1 because XORing 1 with nothing. If somebody asks me what is the XOR between 1 and 2, then we XOR them. Like, it's not like if somebody asks me the XOR of 5 in this range, I should not answer 0, that 5 or 5 should be 0. No. So if I'm on the leaf node, the answer should be the element itself. Let's call it the XOR tree. Okay. And we will say that if I'm on the leaf node, then it's just my array element. Otherwise, I will just take the XOR of these two elements, left and right. This was the XOR. But yeah, I will take the XOR. And you understand that if I XOR something with 0, it doesn't change the answer. So I can just return 0 if disjoint. And if I'm completely within, then just return the answer. And in combination logic, we return left XOR right. Since XOR is associative, we cannot do it for NAND or NOR because they are not associative in nature, right? So we have learned about GCD, max, main, sum, tree. You can think of any other function that is associative in nature. By associative, I mean, let's say this is let's say that star is an operator. If it is equal to A star, B star, C, if this is the case for all A, B, C belonging to my domain, then we say that star is associative. Okay, and segment tree can be created for any associative operator. If you want the iPad notes, just drop a comment, I will post it. Can be created for any associative operator. I hope this is making sense. Now we will learn about updates. So we have learned about querying, we've learned about building, and now we will learn about updates. And we will directly go to lazy propagation or range-based updates. We can do point updates as well, just setting L and R in range updates as same. So we will not be studying that explicitly. If somebody asks me to write point update, I will just say, you know what, this is the range update function. Just set L is equal to R or LQ is equal to RQ in our notation, and that will achieve the point update function. Okay. Okay. If that is clear, let's study about lazy propagation, or I like to call it lazy range updates. Okay. So for example, let's take the sum tree as our reference point. Let's say, I think we have a tree from our previous lecture. Let's take this tree. Hmm. Okay, so let's say we have this tree. Now let's say somebody asked me, please update from let's say 2 to 7 and do +2 in the range. So I want to make every element from 2 to 7 to have a +2. So if that element at 2 is 6, I want this to be 8. This I want to be 9. This I want to be 6. Basically +2 in every value. Okay. So we will start from the segment tree. Again, in order for my range updates to be fast, we will make a lazy tree alongside my original segment tree. I will tell you why. Let's do it let's do it individually first, like the point update way, in order to see how much time does it take. For example, let's say I know I have to update from 2 to 7 +2. Let's tell my segment tree to update this second index and do it +2. What it will do? It will travel. Let me highlight this. It will travel like this, and then this will do +2 here. And then in the next index 3, it will do again +2, then again +2, again +2, again +2, again +2. So you understand, if my query or update query is from L to R, it's taking R minus L plus 1 multiplied by log n number of operations. So in the worst case, if I do it pointwise, individually from L to R, I should say LQ to RQ, then it takes RQ minus LQ plus 1 is the number of element into log of this RQ minus log n actually, because that's the height of the tree. In our case, it will be log of 4n because uh, 4n is the number of nodes in our tree. In the end of this lecture, I will tell you the exact uh, idea behind 4n, which I left in the previous lecture. Okay, so you understand that this is very costly. Like in the worst case, this can be n, and this can be again n, so 4n. So it's n log n. So if it was a general normal array, range updates took order of n. But this segment tree is taking order of n log n. So more. Of course, I do have log n queries, n build, but still, we don't want updates to be n log n. We want updates to be log n or even constant. We will achieve log n in segment tree. So we will do it the lazy way. So let's think about this. What we can do. Let's make a copy. Let's make this smaller. Okay. Now, okay, let me just make it a little bit more small. Okay, and let's make a duplicate value of this. This tree is called the lazy tree. And initially, every element is lazy tree is zero. Mm, but can I just okay, to reduce the size of my eraser? Just give me a moment. Okay, these were already zero. I will tell you why we are filling zeros in our lazy tree. So this is my lazy tree and this is my original segment tree. Okay, now let's say we are told to update, or let's take this question only, update from 2 to 7. Let me just copy this. And let's say this is the question. So please update from 2 to 7 and do plus 2 in the range. So we will just go to my lazy tree this time. Or we can go to the segment tree as well. Let's go to the segment tree and say, okay, what's the first? It's saying 0 to 7. So no, not the responsibility region is not completely within my bound. So makes two calls. So should I make this a little bit bigger for understanding purposes? Yeah, I think I should. Yeah. So initially we are going this and this. Now it's saying 0 to 3, so not 2 to 7, not completely inside. So no. And now we have come to 2 to 3. Now it's completely within. Now it's as I'm doing. Okay, so I'm supposed to fill this entire range, right? Let's do it the laser pointer. So I have come here. Now I'm saying that the responsibility region, that is 2 to 3, is completely within my LQ and RQ. So I'm supposed to update this entire range. What can I do? Either my option is to just update this node or update this entire world. So I will be lazy and I will say, you know what? How many elements are beneath me? 2 to 3. So 3 minus 2 plus 1, that is 2 elements. So I will do 2 multiplied by plus 2, and that I will add to my answer. So 13 plus 4, because that will affect my sum that way, right? And I will say, uh, in this case, we have not updated the values. So I will put plus 2 in this lazy tree that is here. And they will take care of the rest. This is not very evident now. Let's do it the next call here. So let's say the second word is 4 to 7, right? So completely within my responsibility region. Now I will ask this 27. How many elements are beneath me? So 7 minus 4 plus 1, which is 4 elements. So I will do 4 multiplied by plus 2, and I will add this to 27. So 4 2s are 8. So 27 will become 27 plus 8, that is, I think, 35. And I will say, this is okay. And I will say, you know what? Do plus 2 here and plus 2 here. So I will tell my children to do plus 2, but not do it in my segmented. So what it will do is do plus 2 here and plus 2 here, or just 2 in our case. Okay. Now, this is the condition of my tree uh, after this update range. I mean, update 2 to 7. And we have also changed this 27 to 35, right? And we have changed this 13 to, I think, what this is 70. But this has plus 2 in my lazy tree. 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 Now let's assume somebody asks me, what is the answer from 4 to 7? I will just directly come to 35 and I will say 35 is my answer. What if somebody asks me now 4 to 5? Then I will travel from here to here and I will see. While traveling, I will always check, do I have some lazy update that I must do? Otherwise, I am doomed. Like, for example, if there is a plus 2 here, while traveling, I must take care of this plus 2 here in order to go down. Otherwise, all the answers here are wrong. If this lazy thing is not propagated downward, all the answers beneath me are wrong. So while traveling down in my segment tree, I'll always check if there is some lazy update pending. I must do it before going down. Now we have come here. Now it says it has plus 2. So we cannot say the answer is 13. First, I have to do plus 2 in this 13 and then plus 2 here. Update. Then I will say, okay, 13, since when this plus 2 is updated here, it will become 13 plus 2 plus 2. That is 70. And this plus 2 will be updated here. So while we are traveling, okay. So you understand, while we are querying, we are while we are going down, we are taking care of lazy. While uh, maybe updating another range, we are also taking care of the lazy. Let's say this range is updated, and now I'm doing some another update, but I have pending updates while going down, then I must do that before going down. Think about this a little. Just do it for a lot of cases. Like we have updated from 2 to 7. Then we do 5 to 7, then 3 to 4, then 1 to 2. Or do all of this in your head. So what we are doing is, if I can do it on the node, I will just do it on the node. If I'm completely within, and I will tell my children to do their own updates and not go completely inside the tree to mark every possible right answer. This is called a lazy update mechanism. I hope this is making sense. Okay, let me just do it for one or two more cases so that this idea is more clear. So let's assume somebody has told me to, and let's say 2 to 7 is done. So this is my condition of my segment tree. First 2 to 7, and then query has been done. If query was done from 4 to 5, this would have been propagated. So 13 would have become 17. And there will be a plus 2 here and a plus 2 here, right? And if somebody now asks me, what is the update range from 3 to 3, then I will go like this. And I see there is a update remaining. So I will do 3 minus 3 plus 1. That is my, and then add it to my 7. After doing that, I will update my original answer. So first I am doing the pending update, and then I am doing, and while traveling, I am already taking care of all the updates that were here and here, so that the after reaching here, I know that the previous pending updates are done. If there was a pending update here, I don't care, because that this will not affect this answer at all. These two trees are disjoint. I hope this is making sense. Just think about it a little bit. You will get it. Okay. So let's code this down. So we had one lazy tree along with my sum tree. I will tell you how to do it for others or GCD, max, min. You can think about it together. Let's go. So this is called part two, or I should call it the lazy propagation. Okay. Let me just copy this sum tree code. Now we will have a range update. So it will say, it will have an IDX, it will have an LR, it will have an LQ to RQ that I want to update, and it will have a value, val. So if it's plus 2, then I will send value as 2. If it is minus 2, then we send minus 2. Okay. So I'm just copying this function definition. Let's copy this, and I will call this update. Now it will take another integer, that is val. So I will call it val. Okay. Of course, the return type will be void, because after updation, I am not returning anything. And it will never be the case that update is not possible. Okay. Now let's make the lazy tree, and that will have the same size as my original tree. So I will call it lazy sum tree. Okay. And initially everything will be 0. You know that if I create a default vector of int, all the elements are by default 0. Okay. So let's go to the update. If I am completely within, before update, by the way, I should check, like, why after traveling, we should always check if this lazy is disconnected for some reason. Uh, okay, reconnection is successful. Okay, so if it is not zero, so I will check this every time I am doing an update or a query. So if I have some pending updates that after traveling here, after traveling on this index, if I have some pending updates, I must do it. And how can I do it? Either I can tell you how to write the apply function for every this updating this lazy part or applying these changes is called applying uh, applying something to this segment tree, and then it's called, and after applying we just propagate it to our children. This is called apply and propagate. Like this is called combine. And apply, propagate, combine are the things that change from some from some tree to min tree to GCD tree to XOR tree or any kind of tree that you are trying to build, as long as the operator is associative, of course. So let's think. So if it is not zero, that means I have some pending update remaining. So I should do some tree of IDX should be added. How many? So what is my responsibility region? R minus L plus 1 multiplied by L. So this should be must have been added. So this was my responsibility region R minus R to L. So what value should I add? R minus L plus 1. That is the number of elements beneath me, and add it to the value. Okay. And then I will propagate it. I will just say that lazy sum tree 2i plus 1 should plus equal to val. So I have just propagated this val to my children. Okay. Of course, these children must exist. So if L is not equal to R, then only I will do this. If L is equal to R, I am already in my leaf node, so there is nothing to go beneath me. Okay. So this is called the apply logic. And this will change from tree to tree. And I will have this apply logic before this update world as well, okay, query world as well. But if I have some pending updates remaining, and this will not be val this time, this will be lazy sum tree of IDX. Okay, by the way, this will also be lazy sum tree of IDX. So whatever value I have in this IDX, and of course, after this, I will just say that since this has been propagated, so lazy sum tree of IDX equal to 0. Same in this case. So in apply, what we have done is going to my, first we have combined my updated myself. Then if children exist, then propagate it down. This is called the propagation. To children. And then we will say, okay, propagation is done. So I can now set myself to 0. This is the same thing that we have done. So I'll just copy this along with the comments. Okay, this is called the apply and propagation. Now, after this is done, now I can do some things. Like in this update, we can just say that if LQ is less than equal to R, so I'm completely within. So I can just say, you know what, don't update completely. just do it for myself. So I will just say, do it for myself, sum tree of IDX, and I will just say, you know what, do it for the lazy world. Okay, let's do it like this. So what we have done, if I'm completely inside, I will just update myself based on L minus R plus 1 by 2, sum that is. And if I have children, then I will propagate to my children and I will not update my entire world of children. If if it's disjoint, then I have nothing to do, just return. Otherwise, I will just, okay, I'm in the update, right? So I will just call the update because this will have a val. Okay, again, this should be val. So if I'm completely within, update myself and set my lazy sum tree of children plus equal to val. If I'm disjoint, then I have nothing to do. Otherwise, just call this update function L made LQRQ val. And since it's not returning anything, I cannot expect any value out of it. And we don't have to do anything. It has done it for the left, it has done it for the right. Okay. So this is the code that will help me do range updates efficiently. Let's try to do it for our case. Okay. The camera is running. Okay. How long is the stream running? Oh, 30 minutes. So this completes our lazy propagation idea. And now I will teach you the logic behind 4n. Okay. If you go back to, let's go back to the iPad. It's not connected. Okay. So let's say the number of elements in my array is equals to 8. I know that this uh, needs me to take a segment tree of 2 into 8, that is 16, or 15 to be precise. You see, we have 15 nodes in our segment tree. So if n is equal to 16, you can calculate that it takes 31 nodes. So 16, 15 nodes, and it takes 31 nodes. What if n is equal to 9? That will also take 31 nodes. Why? Because let's say 7, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, like 9. Now, we cannot do this like this. We have to have this tree, like this joint set tree here, so that it spans. So this becomes a power of 2. Otherwise, there will be imbalances in our tree. So if it is 9, then 10, 11, 12, 13, 14, 15. So we will have this 9, 10, 11, 12, 13, 14. Sorry, 9, 10, 11, 12, 6, 7. Okay, so it will be 8, 9, 8, 9, 10, 11, 12, 13, 14, 15. So that it can become pairs, and then we can have another node. I hope this is making sense. So we want this tree to be disjoint and balanced in such way. So you see, 9 fours are 36. So always 4 times n is sufficient. Like I will always take the next power of n. So basically, I will take log base 2 of n and I will take the seeding. So if it is 9 here, so this will lead me to 4 because 2 to the power 4 is 16. And that multiplied by 2, sorry, this, uh, I should multiply this by 2 as well. Sorry. So log base 2 is the number of, uh, okay, let's say this is 9, okay? So this, I want, yeah, this is what I want. So power of 2, which is just higher than this 9. This will lead me to 16. And 16 needs 31 nodes. So you see, I always, so 3n for segment tree is not sufficient all the time. So the number of nodes in the tree, uh, I need 2 times that in my segment tree. And the number of nodes is 2 to the power ceiling of log n. So you see that if n requires 2n, and this n, if p is not a power of 2, this p can be up to twice n, like 9 if I have. So it can be around 18, you can think, if it is maybe, let's say it is 32, let's say 33, right? In that case, I have 64 nodes are required if n is equal to 33. So if n is equal to 33, which is the number of elements in our array, this must be scaled to 64 size. And 64 requires 128 nodes in my segment tree. So it's around 33 multiplied by 4. Think about this a little bit, okay? Like the seal power of 2 can be maximum up to twice my number. Or I can say the next good power of 2 is maximum twice myself. And segment tree requires twice of that in order to be sufficiently complete binary tree, I should say. Not complete, I should say full binary tree, because every node has 2 children except the leaves. Okay, I hope this is making sense. That's why we take 4 multiplied by. I hope this logic is clear. We'll stop this stream now, and in our next lecture, since we have discussed lazy propagation, we'll be solving a lot of problems of static range sum queries, dynamic range sum queries, how you can use updates, queries, lazy ideas in order to solve a good number of problems. All of these codes will be available in my video description. I hope this. I hope you learned something. Like, share, subscribe. You can support me through UPI if you want. Have a great day.